Hello, everyone. My name is Dr. Phil Van Hoster, and I am one of the engineering faculty at the Gordon and Jill Bournes College of Engineering at California Baptist University. I'm coming to you today from my virtual lab, as we are not meeting face to face for this STEM program. However, I'm going to give you plenty of examples to look at and to help you understand this wonderful thing called electromagnetic interference. Now, what is interference? Well, typically when you think about interference, you think of something bad, and oftentimes it is. Electromagnetic interference will interfere with your electronic device and cause it an anomaly, not to function the way the designers intended it. So for example, you look at my lab here, and in this lab, you can see a lot of electronic equipment. But you also see up above, you see some fluorescent lights. Those fluorescent lights emit an energy field, and that energy field can interfere with this lab equipment, thereby preventing the equipment from taking proper measurements. All of you have experienced this. Sometimes this interference can be catastrophic, where you have a multi-million dollar or hundreds of millions of dollars piece of satellite equipment that's being launched, and it gets some sort of interference that occurs that causes a failure. Sometimes it can cause deadly failures, and we'll talk a little bit about that. But for the most part, electromagnetic interference has to do with everyday life, and it's an inconvenience. Now, the Federal Communications Commission actually monitors this and puts out regulations such that manufacturers and designers are building and designing their equipment so that they are less susceptible to electromagnetic interference. And there's a whole science behind this called electromagnetic compatibility, where engineers, scientists, and researchers are discovering new ways to make a device function, for example, your phone, which needs to project out and to broadcast electronic emissions, and yet prevent outside interference from causing failures in that. So we'll talk a little bit about that, and we're going to look at how a mechanical engineer gets involved in an electrical problem, and how we're doing something what's called shielding or shielding effectiveness. And how does that shielding, what does it look like? It's a mechanical solution to an electrical problem. We'll go over that. So with that being said, that's a brief introduction. Let's go ahead and get started on some terminology and take a look at some examples.
So as stated earlier during the introduction, this is a problem that demands engineering and design attention. When I go out and purchase something, my expectation is that that product will work. It's going to work the way it was intended to function. There are several failure modes that can occur. I could run out of battery, and that's a failure mode for my device. But a particular failure mode that I am not counting on is something that is caused by an outside interference. So my device should not be susceptible to another electronic emitter. FCC monitors this. Devices are supposed to have particular protection, and this is where the electromechanical compatibility engineer comes into play. The EMC engineer is designing a product so that they can make certain that it achieves the protection that the FCC is regulating. Now, there's a reason for this. One is that, as I said earlier, there can be catastrophic events that can occur, and none of us want to see that. But there is also another reason, and one is that, when I purchase something, I expect it to work, and if I then go into a room, a public setting, and it no longer functions, whatever is causing that failure, in essence, is taking away the value of my product. And that's something that is in the simplest of terms, someone is, or something is stealing from me my product and or my ability or my product's ability to perform the way I paid for it. So in a just and honest society, we need to be able to avoid that. We need to make certain that we are using the tools that we've purchased, and we are selling the tools or the items in a way that we know it's going to work the way we're telling our customer that it is going to work. For example, if I purchased a drill and I was going to put something in my wall, mount something in my wall, my neighbor is expecting to be able to use their TV without a problem. And if my drill is defective and emits a frequency that causes interference, my neighbor is no longer getting the value out of their television, that they expected when they purchased it. But these invisible waves can be much more than just a simple inconvenience, such as a dropped call. They can actually be quite catastrophic. When you have a product that was designed to be life-saving, such as a pacemaker, and that product no longer functions the way it was intended, like it or not, someone's life is in jeopardy. Electromechanical compliance engineers have to take that very seriously and have to take that into consideration. When a device is susceptible to outside interference, the failing of that device could potentially lead to loss of life. Let's take a look at some video from a disaster that did lead, unfortunately, to loss of life. On July 29, 1967, the aircraft carrier USS Forrestal was deployed to the Gulf of Tonkin to provide air support in Vietnam. That morning, EMI interference triggered the launch sequence of a Zuni rocket from an F-4 Phantom into an A-4 Skyhawk. The fully fueled and armed A-4 was being prepped for a sortie into Vietnam, but instead that morning it burst into flames on the flight deck. Its 1,000-pound bombs were exposed to the high heat of the fire, and bomb after bomb exploded before long. That day, 134 U.S. sailors were killed. 21 aircraft were destroyed. And when adjusted for inflation, the cost of the U.S. Navy was over $500 million. Now, the FCC was not the only federal agency that was tracking EMI and the hazards of EMI. In the early days of medical equipment, electronic medical equipment, the FDA, or the Food and Drug Administration, was tracking when they would have failures in the field due to EMI. Between the years 1979 and 1993, they recorded 90 EMI issues that occurred in the field. Now, it's important to understand that this is likely underreported. At the time, electronic equipment was relatively new, and oftentimes users had no idea why it wasn't functioning. Think about how many times that you've had a trouble with your device and you just shut it off and turn it back on, not understanding what was causing the failure. Same kind of a thing occurred in the field. So it was likely underreported, but regardless, you can take a look at this list and you can see that radiated interference, for example, the second column, radiated interference is something that would be caused by cellular phones. And this is whether it's defibrillators, ventilators, or wheelchairs. All of those devices had reported issues between the years of 79 and 93 that were resulting in field failures. In one instance where failure did cause a fatality, a 93-year-old heart attack victim was being taken to the hospital. The medical tech that was monitoring him and trying to save his life hooked up the defibrillator, but unfortunately every time the medical tech radioed or turned on the radio to communicate with the doctors at the hospital, the defibrillator monitor shut down. Essential information could not be recorded and transferred over to the doctors. They could not order any kind of action to be taken while the heart attack victim was in transit to the hospital. And by the time the ambulance got to the hospital emergency room, the patient had died.
All right, so I'm telling you these things not to frighten you. These are issues that occurred over 25 years ago. And a lot's changed since then. The understanding of electromagnetic radiation and the field of electromagnetic compatibility has grown tremendously. Engineers have graduated from universities, gone into research, studied, been hired by the likes of Microsoft, Apple, Ford Motor Company, you name it. And they're there for this intention to confirm that the electronics within a device are going to be protected. The Federal Communications Commission also monitors this. They test everything, and I can tell you from personal experience and witnessing it, if something does not pass through the FCC requirements, it is not shipped. There were times that there were shipments that I was aware of from other companies or other organizations that were sitting in docks because they failed to pass FCC, and the U.S. Customs wouldn't allow them into the country. So a lot has happened, a lot has improved. However, you can see from this that it's really important that we understand what is going on with the electronics that we hold in our hands. So, with that being said, what is happening? So imagine you have an electronic charge that is traveling. An electronic charge is moving in a direction and it is at a constant speed. Well, what happens when that electronic charge accelerates? There is a field that's emanating or radiating from that electronic charge. However, the acceleration occurs and the area near the field, near the charge, recognizes that the speed has changed, but outside or away from that charge, it doesn't recognize it and it doesn't see it. And what forms is what's referred to as a kink. This kink then will cause a wave to radiate. Now, it's kind of interesting to talk about these things in terms of waves because it helps us to understand how then can we take this unseen item, this unseen phenomenon, electromagnetic waves, and conceptualize it as something that is physical. You've all seen waves, you know the power of waves. I'm going to take a few minutes now to say, let's take a look at some things that show or demonstrate the power of a wave.
So let's do a recap here. We know a radiated field is coming off of the charged particles. As those charged particles change in acceleration, or change their speed rather, and they accelerate or decelerate, it causes a wave to come off of it. Now, a very common term that needs to be understood is the frequency of that wave. So what is the frequency that the acceleration is changing? That frequency will issue a wavelength, or what is the distance between one wave and the next. That's referred to as wavelength. And we end up then with a transmitted frequency. The whole point of this is to figure out a way to prevent a device from being susceptible to an outside interference. Wavelength is what determines how susceptible a device can be. So different frequencies, or the distance between peak to peak on that wave is the frequency. So the different frequencies will determine what is going to penetrate through a shield. The higher the frequency, the smaller the wavelength from peak to peak. The smaller the wavelength, then the smaller hole that it can get through and pass through and inhibit or cause problems with the device that is susceptible to that particular frequency. So how do we protect a device? Well, we want to build a shield around that device. The shield is going to be a conductive barrier that will encase the circuit, and thereby any kind of energy, EMI energy that's outside of that shield will hit that shield and will bounce off. Same can go for any kind of energy that's inside that shield will hit the shield and bounce off or remain contained within the shield. That's the whole point of this, and that's what engineers will look at. How do they create a barrier? How do they build this shield so that they can isolate the device and protect it? Oftentimes, the easiest way to understand anything is to think of physical representations. So, for example, you have a wavelength that we talked about, and the wavelength would be the distance from the peak of one wave to the peak of another. This wavelength will then determine the frequency of each peak. So the shorter the distance from peak to peak, the greater the frequency that you encounter a peak. Now, what might be a physical representation of a frequency? One way to think about it is if you think of a solid and you think, say, of peanuts, And now you have peanuts, and you're going to try and contain those peanuts into a basket or something. You would not have a basket that has holes larger than those peanuts. Or if you take a fluid, say something like honey, the fluid has, honey has a higher viscosity, it's thicker than water. So one way to associate a physical representation with the frequency of an energy field is to think about the viscosity of a product or of an item. Honey, which has a high viscosity, would be the equivalent of a low frequency. The distance between the wave peaks are greater, and therefore you don't need to have a container that is perfectly sealed all the way around. Whereas water is something with a low viscosity, and that would be the equivalent of a high frequency energy source. And you need to have a container that then is fully sealed all the way around. There are no holes that it can pass through.
All right, let's go back into, actually, instead of the mechanical engineering and ECE virtual lab, let's head off into the virtual chemical engineering lab and see what this looks like. Okay, so here we are, the chemical engineering virtual lab. And one of the things I want to talk about is to kind of give you an idea of this physical wavelength. So I have here before me, I have 3 different size salts. I got your regular table salt. This is something you're all familiar with. We'll consider this to be a high frequency type of wavelength, or a high frequency wavelength. I got here some kosher salt, which is larger salt, and we're going to consider this to be a medium frequency. And then I've got my lovely ice cream salt, which is a low frequency equivalent. Now, when we're looking at this and we're saying, okay, for a low frequency equivalent, I got an item here that's got some fairly large holes. Let's see if those holes can prevent and protect that low frequency product. And as I pour it in, sure enough, nothing can escape through on that. That low frequency cannot penetrate through these small holes. So that shields it quite well. However, if I go to a medium frequency similarity, as that goes through, that passes right through my shield. And of course, a high frequency equivalent, it's not even going to be close. It's just going to go right through. It's like it's not even there. And that's how a shield can have a certain shielding effectiveness based on the aperture size. And you saw it here with just something as simple as salt. If I change my shield to a sieve with tighter, with a much smaller apertures, yeah, I could still use it on the low frequency equivalent. And yes, holds it just fine. Nothing passes through, stable. I can even use it on my medium frequency, and my medium frequency locks through and nothing passes through on the medium frequency. There's nothing there. But when I go to my high frequency equivalent, just the regular salt, and I pour it through, it passes right through that as well. So even this aperture that's shown on this sieve, this aperture size is too large for a high frequency. Now we're going to talk a little bit about how determining the aperture size in just a moment. Okay, let's get back to figuring out what we're here to do, and that is what type of shield will prevent this energy, this electromagnetic energy, from harming our device. Okay, in order to do that, that shield, one of the things you think about, you think, well, let's just put this thing into a vault, lock it up, and seal it all around. We'll weld all the seams, something like this. Well, that's true. We could do that. Unfortunately, most of our devices need to communicate. They need to communicate with the outside world. They need to communicate with you. They need to communicate with some other components. So that's not all that good. Here you can see we have cords that need to come out. We have other kinds of antennas that are traveling, that are transmitting. So there's a lot of radiation that's going on that's effective and valuable radiation. But there's also radiation that's bad, and we want to isolate that particular bad radiation or those bad emissions. What is the frequency of that bad emission? And let's lock that down. And that's the neat thing about shielding. we only have to worry about the one that's bad. We only have to worry about the frequency we don't like. And if we can build a particular shield that only blocks that frequency and nothing else, we've accomplished a massive part of our goal. Okay, so in order to do that, we need to know that frequency. Now there's a neat way to calculate that, and let me show you that right now. I grab my tablet, let's go ahead and start drawing, and I sketch out this curve, which is just your typical wave. I'm just drawing a wave. Over here you can see this is referred to as the crest. The peak is the crest. And down below is referred to as the trough. Now, from peak to peak is the wavelength, commonly referred to with a lambda sign, but the same as from trough to trough is also lambda, which is the wavelength. Now, the wavelength equals the velocity, v, in meters per second. This is the velocity. Divide this by the frequency, and this is in unit of measure of hertz. Hertz is 1/2. This is the frequency. All right, so now the good news is that for electromagnetic wavelengths or waves, the velocity is simply the speed of light. This is commonly referred to with the letter c. Great news, speed of light. This is a constant, 2.98 times 10 to the 8 meters per second. Also often called just a lot of people just call it 3.0. Easier in calculations, you're just going to say it's 3.0 meters per second. All right, so that's great news because now I have one constant, I have two unknowns. Now, if I want to determine my frequency, I can do that with the wavelength. If I want to determine my wavelength, I can do that with my frequency. Now, you can see in this chart here, these are commonly measured areas. These are this kind of gives a picture, shows you how the wavelength changes depending on the frequency. And you can see right there where ultraviolet light is found. And you can see that this is the light spectrum right here in the middle. Okay, so we see on that previous chart, we have a visible spectrum, which defines a wave. And that wave has some sort of length. That length has some sort of frequency. So we've seen that. Now, let's talk about things that actually we experience every day. So for example, if you take a look at this chart here, we're looking at things, I want to know the frequency of certain bands, like the AM band. And if you look here, the AM band has a frequency of 300 kilohertz. Well, 300 kilohertz, when I take that with the speed of light, which I know, from that I can convert now and find what is the wavelength. That's a wavelength size of a football field. Well, you know, it doesn't take much to shield a wavelength the size of a football field. And that's why when you go underneath a bridge, pretty quickly your AM band will fuzz out. Now, if we move further down the spectrum, we can get to the FM band. Now, the FM band, that has a much higher frequency. That frequency is 30 megahertz, which again, when we convert that into our wavelength size, we can see that it's a much smaller wavelength, still big as a house. But that explains why when you go underneath the bridge, that wavelength is small enough to still access your radio in your car and still transmit. As we move further down, we can see that we have a high frequency in microwaves. Now, when we get to microwaves, we start to get to something a little bit interesting. It's not just for cooking food. Just past microwaves, we start getting into some communication bands. And these communication bands have wavelengths that start to get smaller. And you can see a communication band like a satellite radio or just a walkie-talkie kind of communication. Now we're getting into frequencies that are greater than 300 megahertz, and they're approaching the gigahertz range. And we have thereby wavelengths that are getting smaller, approaching the size of a tennis ball. Still pretty big, still pretty easy to shield. In fact, oftentimes the problem is it's too easy to shield, and so they stop working when you go into a bedroom or when you get into the car and close your door. That's a problem. But as you see, we get further down into smaller and smaller. We get into what are referred to as millimeter waves, and these are atomic size. Now we're getting into the world of ADAS. ADAS is the auto driver assist that you have or your parents may have in their vehicles. So these are millimeter waves, and these millimeter waves need to pass through and need to be able to access the vehicles in front. And because there's such a high frequency, low wavelength, small wavelength, they can travel great distances. And that's very important when you're trying to detect something. So now shielding around these becomes a little more difficult because you want to shield something that has a very small wavelength, and yet you still want to be able to access the information that's being transmitted. Now, some people might say, hey, the easy thing is let's just throw our device into a massive welded box like something like this. But as I've already alluded to, that's not a good solution. It's not a good solution because now we can't use it anymore. And if it's not functional, why buy it? Why have it? Can you imagine if you bought a $1,000 television, you mounted it on your wall, and then after you mounted it on your wall, you took a big old box and put it over it. And that box muted sound and vision. And then you sat down on your couch and smiled to watch a football game, which you couldn't watch. So, nevertheless, a shielded box is what we're looking for. And we need to determine what is the shielding effectiveness. And we do that by enclosing the device. So if you look at this slide here, what we have is we've got a sensitive device contained within the box. The box is a shielded enclosure that is grounded. The grounding allows for the electrical current to pass through and create a force field. If it's not grounded, then that force field cannot be intact. So you have a signal, a violating signal, which is denoted as F1, and it comes and it hits that box and it reflects off of it. So you have reflection loss. Now, depending on what the material is of that box, you will also have some pass-through. That pass-through then has absorption properties, and so then you have absorption loss. That's a second. So your total shielding effectiveness is going to be your signal, your input signal, divided by what your transmitted signal is. Or in essence, you got your shielding effectiveness from your reflection plus your shielding effectiveness from your absorption. So those are the two determinants of your overall shielding effectiveness.
So let's take a look again at our whiteboard and see what shielding effectiveness is. Shielding. So we're interested in shielding effectiveness. Oops, got an E in there. Let's get rid of these two here. Cut out these S's. E, S, S equals 20, which is a constant. We're given 20 log based 10 of lambda over 2L. Now what is lambda? We know is our wavelength. What is L? Well, if we have a circle or a hole, and then it has a diameter, which the diameter is the longest opening, that diameter is the length L. And if we have a slot, then the longest opening is L. We're interested in the maximum amount of opening, whether it's a circle or it's a slot. Now, from this, then we can say, okay, well, our wavelength is going to equal, we know wavelength equals C over F. That's an unknown. We got to figure out what wavelength is. Now F is our frequency. So F equals frequency. And C is our constant speed of light, 3 times 10 to the 8th meters per second. frequency is in unit of measure of hertz, or 1/second. And the last thing we need to note here is L. L is length, or longest dimension of our opening, and this is in unit measure of meters. So it's important. Most of these are known. We know the speed of light. We can measure the length. We can measure the frequency. We can figure out lambda, and we can then figure out shielding effectiveness.
All right, so what you've probably realized is that this is just an equation with some unknowns. And in fact, if you were to substitute some values into those unknowns, you could create a graph and have a broad spectrum of results. So take a look at this graph. Basically, this is a logarithmic graph. It's been broken down, and it tells you what is going to be the shielding effectiveness for a particular aperture size at a particular frequency. Great news. You can look at this and you can say, okay, I need to have this particular shielding effectiveness. So this is what I need to have as far as any kind of opening. So for example, you can also go in the reverse and you can say, I got to have 100 dB of shielding effectiveness. I have my violating frequency, or my concern frequency, is 1 gigahertz. If I have to have 100 dB at 1 gigahertz, if I then take a look at my aperture size, I'm looking at aperture size in the area of 1 micrometer. Pretty small in order to get that. Now, you probably are asking, well, what is a dB? I don't even know what's happening there. So imagine this. Remember we talked about waves at the beginning, and those waves are pretty huge when we look at ocean waves. Similar to what will occur in a lot of bays or dock areas, or even at a swimming area, you'll have a breakwater that goes out, a breakwater reef that goes out into the ocean. That breakwater reef is such that when the waves hit that reef, it breaks it down and drops the amplitude or the energy of that particular ocean wave. Shielding effectiveness is the same kind of a thing. What you're saying is, hey, I have a energy source that is radiating. It has a particular amplitude of energy that's coming through. I want to reduce that energy by a certain amount. And that's what shielding effectiveness is. I am reducing that energy by 20 dB, 40 dB, 100 dB. And that way I know my device will continue to perform. So if we take this into consideration, if you were to look at this graph and you were to say, I need to do a shielding effectiveness for Bluetooth. I have some Bluetooth that's going on, and it is going to be impacting my device because there's a lot of Bluetooth around. I want to make sure I've got some other type of device, maybe it's Wi-Fi, and I want to make sure that any Bluetooth devices that come in the vicinity of my Wi-Fi router do not impact my Wi-Fi router. So I need to shield for any kind of Bluetooth frequency. Well, Bluetooth frequency is 2.4 gigahertz. So take a moment, take a look at this graph. I'll blow it up for you so you can see it a little bigger. And tell me if you need to get at least 80 dB of shielding effectiveness, what is the smallest size aperture that you can have exposed? All right, let's open this up and take a look. Okay, now the equation isn't quite done because rarely do we have just one hole. We usually have an array of holes. So our shielding effectiveness equals 20 log 10 of lambda over 2L, where L is the greatest length. But then we subtract, we add to this equation a reduction in shielding effectiveness when we have an array of holes. And that reduction is calculated as 20 log base 10 of the number, n, the number of holes we have. And n, this is the number of holes, is the number of apertures within a half a wavelength. So you can see from looking at this this could be pretty dramatic. You have an array of holes for ventilation, and that array of holes are such that there's so many within a half a wavelength, and you've just completely eliminated the effectiveness of your shield for the frequency that you're concerned with. It's a very, very big concern, and yet it's something that you have to take into consideration as well. So prior, you did a calculation, or you looked at the chart and you said, hey, here's my chart. This is my chart with based on my shielding effectiveness, which would give you the first part of this equation. And then you have to take a look at the size of your holes and the how many holes are within a half a wavelength, and go through and figure out how that will then reduce your shielding effectiveness. All right, so if we want to try and figure out what's it going to be for Bluetooth, we take our chart, this is what the assignment you had earlier, and we know the Bluetooth that's roughly 2.4 gigahertz. That's what Bluetooth frequency is, which is right about here. We draw a line straight up to where it intersects our 80 dB, which was our objective. And we can see that in order to achieve 80 dB, we have to have our maximum aperture is 10 micrometers. So shielding effectiveness at 80 at 2.4 gigahertz frequency equals 80 dB when max aperture equals 10 micrometers. And for your reference, in case you don't know, 10 micrometers is the equivalent of 0.004 inches. Human hair. That's about what we're talking about here, the size of a human hair. So it's pretty tiny as your maximum. It's practically a continuous contact with no holes. Now, obviously, if we had holes, or if we had an array of holes, that would make it even worse because that would pull down on the shielding effectiveness. And this is not to say that you can't still have an aperture at 10 micrometers. It's just that your shielding effectiveness is not going to be 80 dB. Your shielding effectiveness, if you have an aperture, you can see from the chart, if we were to have an aperture of 1 millimeter, then my shielding effectiveness goes down to about 40 dB. It may be perfectly acceptable to have 40 dB shielding effectiveness. The energy from the radiated wave may not be much greater than 20 dB. So having 40 dB shielding effectiveness pretty much knocks it out. However, when we're in the design world, we're typically trying to design things around 60 to 80 dB of shielding effectiveness when we're working on shields. Okay, let's go ahead and put this into practice now. You all should have received in a kit where you have a fence and you have two covers. Some of you may have gotten it so that you have already a fence with the cover installed and a second cover. Those are the lucky ones. Regardless, first thing you need to do is you need to have a fence and a cover, and you need to install one of the covers, and you need to go through and do interlocking fingers. One finger on the outside, one on the inside. And that has to go all the way around on the sides as well. If I do something like here, that's a mistake. I need to fix that and make sure that I have a finger on the outside as well as the inside. Do that all the way around, and you'll end up with something like this. Now, if you recall, we did some measurements, and in order to get 80 dB, we found that for a 2.4 gigahertz frequency, we had to have a hole or an aperture that was only 10 micrometers. That's way too small. We would need tape, foil tape that wrapped around this. So instead, you can see that I've got here some holes, and I went ahead and took a measurement with some mics on what that is, and it's just under 1 millimeter. Again, if we go back to our chart, 1 millimeter hole for 2.4 gigahertz, we should get 40 dBs of shielding effectiveness. I think that'll be enough. I'm a little bit concerned that this is putting out a radiation a little bit higher amplitude than that, but we'll give it a shot and see how it goes. Now, before you get started, you're going to want to take your Bluetooth speaker and your phone or some other device, iPod, iPad, and you're going to want to link those up. So you're going to want to pair your Bluetooth speaker with your phone. After you have it paired, then you can go ahead and start some music, whatever music you want, and we will move on to the next stage, which will include we're going to take your phone, and we'll be putting it inside the shield. So I'll go over that in just a moment. But first thing, take a few moments. Go ahead and pair your phone to your Bluetooth speaker. And you can actually use headsets if you want, like if you have AirPods or something like that, you can just pair it that way. It's just a matter of Bluetooth. It's just got to be Bluetooth, and then you can go ahead and start music. All right, so I'll give you a few minutes to go ahead and do that, and then we'll get rolling. So with that being said, go ahead and start your music. Once you got your music started, you can go ahead and place your device inside the shield. After you place it in the shield, go ahead and start putting on the cover. That cover's got to go all the way around. It's got to make contact with the fingers all the way around. So I'm going to go ahead and start it on one side, get it down, the side, both sides, and make sure that I get it in all the way here. And there it goes. You can hear it's trying. It's really trying to get through. So, but this shield is working with this phone. There I am getting the shielding that I need and the shielding effectiveness that I need. Once I go ahead and reopen it, boom, automatically it starts happening again. Now you can hear it's a little bit, sometimes it's on, it's off. I have to actually put pressure because I have to make sure there is good electrical contact. You may need to also. This shield's gone through a little bit, and some of the fingers are a little bit distorted. But nevertheless, I'm able to get this to make contact all the way around. And as soon as I release it and open it back up, once again, it goes out just fine. So you can see that that is a shield that is functioning. It is working, and I am getting my attenuation and shielding effectiveness, and I hope you are too. All right, so let's wrap this up. Here's a few things that you learned. These are things that are your takeaways, your learning outcomes. First, you've learned how to associate EMI interference with a radiated field. This radiated field is monitored or is characterized by a wavelength. The wavelength is a factor or is a ratio of the speed of light over the frequency of those waves. When you know we can measure the frequency, when we can measure the frequency, you can determine the wavelength. When you know the wavelength, now you can determine how to create a shield that will protect for that particular frequency. The example we used Bluetooth, the frequency for Bluetooth. How do we create a shield that prevents a Bluetooth radiation from affecting our device? So by understanding that, you then recognize the way to create this shield. The factor that comes into play is the size of any kind of aperture or hole in your shield, because the wavelength can squeeze into any kind of opening. I used examples such as physical examples so that you can see from a physical example how that will then go through or pass through any kind of hole or opening. The larger the physical example, the larger you can have a hole and still protect from any kind of pass through. So when we did our example, when we looked at what did we need for Bluetooth, which is 2.4 gigahertz, depending on how much shielding effectiveness we tried to achieve. The example that you worked out was to achieve 80 dB of attenuation of your shielding effectiveness, and that showed that you needed a hole no larger than 10 micrometers, which is the size of a human hair. Well, our shield wasn't that perfect. We would have need to tape around it and wrap it up with some copper tape. But instead, our shield had holes in it already, and those holes were roughly the size, just under 1 centimeter in size. 1 millimeter in size. So because they were just under 1 millimeter in size, we looked at for the 2.4 gigahertz, we would have a shielding effectiveness. Still, we'd have a shielding effectiveness that showed up on our chart. And that shielding effectiveness was roughly 40 dB, which turns out to be enough. The energy that's coming off from our transmitter to our speaker was not greater than that, didn't have an amplitude greater than that. And sure enough, when we closed our shield, we separated and cut off that shielding or that radiation. So that's a lot about EMI, electromagnetic interference. And it gives you a little bit of an understanding of how electromagnetic engineers, compatibility engineers, will go ahead and analyze a problem and correct it. With that being said, I thank you very much for joining. I hope you appreciated it, and I hope you understand it, and we'll have a little bit of time for some questions.